All right. Welcome, everybody. This is the second monthly meeting that we're having for the DSGT ARC group. Today is going to be all about modeling. So basically, we have done EDA in the past meeting, and that was all about just understanding your data. And from that, we have hopefully built some nice models that we can share the results. And we're going to share it across the entire group today. So, little agenda for today. Yeah, housekeeping items. I don't have that many housekeeping items besides making sure that you guys have pace access and you have basically everything good, like nothing out of the ordinary. And then we're gonna just dive into the modeling presentations, and then I'll finish with the what we're gonna be talking about in the next meeting. So let's actually dive in and just talk about the presentation. So today, the first team presentee is going to be BioAsk.
Hello. Yeah, so I'm Xuying, so I'm represented our team to present for the Bell ASQ. So first, yeah, just like a recap of what our team is doing. So we have is the large scale biomedical semantic indexing and quantity, and this is divided by phase A and phase B. And then the phase A is we are giving the questions, and then we begin with the user query processing. And then we need to respond with the top 10 list of the PubMed ID and also the text snippet. And then there's actually a phase A class between A and B, but it's also the question, but we need the also generation. And then like it's similar to the phase B. So it's it's giving the same questions, but then we are given the golden articles and snippet, and then we respond with the exact answer and the ideal answer. And then here are two type of the answers that they are different. So for the exact answer, it will be the directly response. And then the ideal answer, it will be like a summarized paragraph. So for example, like the yes, no questions, you will a response with yes, but then you need to like answer like a little bit paragraph too. Um, yeah, can you go to the next slide? Yeah, so this is like our like updated pipeline. So we'll have like a version already, and then this is like the current version, and we might still like modifying it. So first like start with the phase A. We begin like with the user query processing, and then we have the simple queries and the keywords, and then we retrieve the candidate document using the BM25 model. And then from here, this is like the update we did. Before we have a full knowledge graph, but then um, the results was kind of getting worse. And then so we just give like a lightweight knowledge graph. So we extract like simple relationships like such as the X activities Y or X associated with Y from the text. So this can help expand the query, the semantics. Um, and also we added the re-ranking, and also with some additional signals such as the mesh term and the title overlap, like for the entity match. And yeah, so this will give us like the total output. And for the phase B, so we were already given like the gold snippet. So we just still apply the ranking and the filter, and then like we are followed by the question style answering because we have different question types. So we handle them to ensure like the output is matching the bio and skewed format. And also we had like the large language model based refinement, and we use the open file, and then like also how the fallback to handle, and we also like clean the output from the language model to standardize the language, and yeah, so that will help be the output for FISB, the JSON file. Can we go to the next slide? So here's showing some results we had like from different steps. So we have like the baseline the retrieval, like simple retrieval is 0.55, and then yeah, we also have like vertic tick loop, so that's adding a little bit, but it didn't much, so it was removed. And then we had the lightweight graph that's like pushing to 0.5, almost 0.6, and then we also have the title overlapping and the mesh scoring, so it was similar. But overall, like the combined system is 0.36, and a mean average position at the top 10. And for the phase B, we have different types, and then we have for different types they also have different metrics. So we are still working on optimizing the phase B, and we may do like a fine tuning with the data we have for the open bio-large models, and it's yeah, we're still working on that. So the factory question is not so good, and like the fine tuning shows a little bit improving, but we're still working in the progress of that for the different types. Yeah. Okay. Yeah, that's all. I think it's the time of up to. Yeah.
Oh, awesome. Thank you so much. I believe that the next one, yeah, we have a lot of groups to present today, so we're not gonna do questions during the presentations. You guys, if you guys have any questions, feel free to post them on Slack after. So next one is check that task 2.
Hi everyone. I'm Stella. For today's presentation, I'm going to present about the system architecture, benchmark, and metric evaluation, as well as a quick recap from last presentation. Here's a quick recap. There are 3 tasks in CheckThat, and they are logically related. Ideally, the output of task 1 is the input of task 2, and the output of task 2 is the input of task 3. However, to avoid data leakage and keep a baseline, the competition organizer fix and specify the input of each task. As for task 2, the goal is to rank the reasoning traces and output the final verdict from the ranked reasoning traces. And there are 3 languages in task 2. The right side is one sample from the JSON format. There was a mistake in my last presentation. Actually, this is a sample from the validation dataset rather than a training dataset. In the right bottom, I added illustration to avoid confusion, as someone asked me how to understand the input of the dataset the week before last week. Next, I'm going to talk about the system architecture. There are 2 processes, the training processes and the inference process. If you have some experience in test time scaling, that's good. If not, that's fine. Test time scaling is an approach that allocate additional computational resources at inference time. So while testing test time scaling, one advantage of TTS is to improve efficiency. For the training process, here is a quite common flow. The base model is the transformer model, and the loss function is binary cross entropy. As for the base model, I'm now experimenting with open source models like NAMA 3.2 3B and NAMA 3.1 8B. Other models like DeepSeek R1 and OpenAI can also be experimented for further implementation and evaluation. For the inference process, to further improve efficiency, assigning complexity in data pre-processing is done. If we can see that if the claim is relatively simple and not complex, then adopt the single-shot prediction directly. If the claim is complex, then load token from previous pre-trained model and then apply the best of strategy. When I did the literature review, I came across some concepts like ORM, which stands for Output Reward Model, and PRM, which stands for Process Reward Model. And I found that the entire flow related with the best strategy is sorry, I need to meet. Sorry, just interrupt. Why process a reward model? I think it emphasized that the ranking of reasoning traces is based on evaluating each individual step of the reasoning traces rather than the final output of a large language model. And this is related to the majority voting. I will talk about the majority voting soon. So here comes the key question: how to optimize. I explored and did some experiments, like the best of strategy rather than majority voting. Here is a scenario that it's possible that the major of the response given by the large language model are in the wrong track. Sorry. So in this case, the majority of voting won't work. Another implementation is to combine best of strategy with a global threshold and majority voting. Although a global threshold is not quite good, it did have some effect. And another optimization is the base model. I've tried some open source models like Llama 3B, and now I'm trying 3B, 8B, and DeepSeek R1. For next slide, about benchmark and metric evaluation.
Hey, Stella,
Here
you're
is
already at 5 minutes. Would you mind trying to wrap it up to be cognizant
yeah,
of everybody's time?
yeah. Sorry, I'll go it really quick. So here's a current term benchmark. I didn't draw the flow myself. I just quoted from the paper. So so the benchmark is not required actually. And for the metric evaluation, we use the weighted F1 score and yeah, for the result. This is a part result from my exploring, and for some thought and next step, and I think it's heavily rely on existing LLMs. And for next step, I'm going to do further comparison with different optimizations. Yeah.
Cool.
So
Awesome. Thank you very much for presenting. Next one is eRisk.
All right, hello, can you hear me?
Yes.
Okay. So I'm working on eRisk task 1, and just a quick recap of what the challenge is about. It's essentially building a system that can determine depressive symptoms in AI personas through real-time conversations. Yeah, so the personas are released weekly. The submission deadlines are every Sunday, so they really encourage constant iteration experimentation. So improving from what the system I had around a month ago. What I did is the main change is I shifted from a single model into a multi-agent framework. So before I had like a single LLM that was doing the conversations, doing the scoring, and outputting the final result. But what I noticed is there was a lot of drift, hallucination, and inconsistent scoring. The conversations would vary wildly across different runs for the same persona. So instead, what I did is I read a bunch of papers from the same ERIS task last year, and I noticed that a lot of them were using multiple agents with specialized jobs. So that's what we have here. You'll see in the flowchart, we have three agents, I guess two and one layer, which is the orchestrator. But first, you have the interview agent, which essentially handles asking targeted questions to the AI personas and adjusts to responses, and it stays within the turn budget. And then we have the scoring agent, which reads the conversation every turn and then scores the BDI2 symptoms on a 0 to 3 scale, and also assigns confidence levels per symptom. And then I insist on adding this extra layer to kind of orchestrate or coordinate the interview and scoring agent, because sometimes based on what the scorer is saying, we want to tweak the questions that we're asking to the AI personas to target symptoms that might be undercovered. So what this orchestrator does is it's not AI, it's not an LLM, it's just pure logic. It decides which symptoms to probe based on what the scoring agent is essentially feeding them. And it also stops the interview after major symptoms are covered or the max turns are reached. So it handles those two tasks. And the goal for this type of framework is to try to maximize the symptom coverage in the fewest turns possible, because in the actual scoring of this task, that's a few things they prioritize. And taking this system, I actually used Pace to run a batch of 30 interviews per persona, and then used aggregation algorithm to pick the three most reliable runs for the actual final submission that we have to submit every week. And I'll get to that in a second. So next slide. Yeah, so here are some key algorithms that I use to kind of guide the interviewer and guide the LLMs, in addition to just letting them run with a prompt. So the first one is like a Weaver-like aggregation. So what this does is it's actually inspired by like the Weaver paper that I think Anthony sent in the Slack, and he mentioned to take a look at that and try to apply it to this case. So what I did is once I have all of the samples, instead of picking the run closest to just like the median score, which I did in the past, what I did is I calculated like the pairwise symptom agreement across all samples, and then for samples that agreed more with other samples, they have a high reliability score. And then I use that reliability score as a weight to calculate essentially a consensus profile for every symptom using a weighted median. And then once we have this consensus profile, we pick the top three samples that are closest to the consensus via L1 distance, or just like the absolute difference between each of its symptoms and the consensus. The second one is a dialogue tree. Essentially what it does is it kind of standardizes the opening of the interview, because I noticed that if I just let the interviewer agent run, it just hallucinates a question, which is very bad, right? We want it to start very consistently and be able to like control the flow of the conversation. So this is just a pre-computed question bank organized by symptom cluster, starting with the root question. And I used BM25 to match responses to symptoms to navigate down the path of this dialogue tree for follow-up questions until the dialogue tree runs out of questions or there's no good match. Then we fall back to the interviewer agent. Just quickly going down here, we also have the labeling functions. That's mainly for the orchestrator to identify which symptoms are mentioned in the responses, so it can know to follow up or to explore like more symptoms. Yeah, and the sampling strategy I already went over. Okay, so just some quick comparisons. Next slide, please. Oh, could we go to like skip a few slides? I think it was past this. Yeah, it was above. Yeah, it was. Yeah. Okay, so just comparing really quickly, the baseline, which is just using GPT-5 Nano for both the interviewer agent and the scoring agent, versus the algorithm assisted open source models, you can see that with the algorithms plus I guess, a more inaccurate model or like a free open source model, there's actually lower variance in the algorithm assisted model, which means that those techniques those implementations earlier are reducing the standard deviation of the BDI2 score across most of these personas. And next slide. Yeah. And here's just a scatter chart of like each persona. And the x-axis is the BDI2 symptom total score that the baseline outputted versus the new ones. And if they're matching, they're going to be close to the y equals x line. And so far, other than persona 10, which is an outlier, they are pretty close to that line. But one thing I did notice is if you look at the histogram on the right, the new system with the free LLM model, the Gemma 27 with Weaver and all of those algorithms, does undershoot a lot of the symptom scores compared to just running GPT-5 as like a wrapper. So that's something I do have to investigate, although this task does not give us ground truth data sets for anything. So I'm not sure. I have to look into it, but I'm not sure if it's actually undershooting or if the paid model, if the baseline is overshooting. So that's one key consideration here. Yeah.
Cool. Awesome. Thank you so much, Victor.
Yeah. Thank you.
Awesome. I think next up is also eRisk Task 3. I think David.
Hello everyone, thank you Victor for presenting. So this is like a quick update of task 3. This is track style ranking tasks. Basically, they gave us a collection of sentences from Reddit related that maybe or maybe not related to um, attention deficit disorder, and the goal is to rank them depending of each one of the 18 symptoms of the HRS self-report scale. Right now, what I have done using Pace is I implemented a BM25 baseline that basically does lexical matching compared to the relevant words in each one of the symptoms. This is essentially first step in any other further modeling approaches. This is a scalable model since it doesn't rely on dense embeddings, and it has high recall, which means that it there's a very high chance that it will retrieve relevant documents. But there are downsides to that. I think we can move to the next slide. Yeah, as we can see, there's an example of one of the symptoms. We can see it gives it a score of 10. Um, we're talking about the question, how often do you have trouble wrapping up the final details of a project? And the sentence that it gives the ranking is that sounds like a surprisingly challenging project. So it's basically looking for the words without, taking into account other elements like self-referential content or any semantic closeness to the words, right? Right, next slide, please. Yeah, as I was saying, uh, the statements are generic. There's no context to the statements. There are no descriptions of behaviors of that are evidence of the attention deficit disorder. There's a like very high there's a high instance of false positives that are retrieved by BN25. Uh, uh, under this circumstances, we make a few assumptions. We we assume that self-referential behavior will retrieve sentences that are more relevant, and we need to look for sentences that are semantically aligned with the queries for each one of the 18 symptoms in the questionnaire. Next slide. So let's recall the problem setting. This is a zero-shot task. We are not provided with training data. We have to rely on other elements. In this case, the quality of the retrieval, heuristics, semantic similarity, if and model reasoning with language models. Following this first uh, step in the modeling, I will proceed with three candidate submissions. I will first I will apply self-referential weighting. I will apply semantic re-ranking and LLM-based re-ranking, which is basically a prompt that you send all the whole context of the retrieval to the model, and the model decides by a prompt which sentence or which document is more relevant. Yeah, I think that's it for my presentation. Thank you.
Cool. Awesome. Thank you very much, David. I believe next up is Finn Evil.
Yeah, I could go for Finn and Evo. Hello, I'm Justice. I'm going to represent today for Task 1 problem overview. So from last time we spoke last month, just getting a recap of the problem, we're doing multilingual financial question answering with knowledge retrieval across multiple different languages. So we have seven set of languages that we have in that we get questions in, which is in Arabic, Greek, English, Chinese, Japanese, Spanish, and Hindi. And the goal is to basically retrieve relevant financial knowledge to support the correct reasoning and answer selection. And that's kind of the goal that we kind of want to go through with on this to be able to correctly answer these questions across multiple languages. So since last meeting, we've taken a look at a few papers, and specifically, we've looked at the papers that were set down for the data sets. And as shown on the right, prior work demonstrates that the model performance varied significantly across financial tasks and languages. And this was especially shown in low resource languages like Greek. So we had this challenge where we also seen that standard retrieval failed to reliably return relevant language consistent knowledge um, as financial concepts vary across languages. And then also we've seen that direct translation from a strong language like English can also distort the original meaning. And then we also seen that dense retrieval suffers from cross-language noise, and then imbalance in which we have maybe dominant languages that overshadow others. So as this result, the retrieval often returns similar but incorrect or wrong language examples, which negatively impacts the correct reasoning and answer selection as a whole. So we can go to the next slide. So in order to address this, we modeled the problem instead as a multilingual example retrieval problem, as stated above. And for this one, we used the BGE M3 multilingual embedding model. As you can see from the right, it supports 100 plus languages, so it's multilinguality. It's multifunctional, as it provides multilingual and hybrid retrieval. And then it also enables dense retrieval for us and provides sentence level and passage level of granularity. So initially, we used a single global Facebook AI similarity search index. But as shown in the diagram, queries and examples are encoded into a shared vector space, and that retrieval is performed based on that similarity. But that approach introduced interference where similar but incorrect language examples were retrieved when we did our runs. So to fix this, we introduced language-aware routing. So queries are detected to specific language indices instead of one single global index. So we have the ability to have multiple languages within that index that we have and then we do the top five nearest neighbor retrieval. So currently we have language aware index selection for Greek, Spanish, and we have one for global. That's for the other languages. At first, we've only had the training data for Arabic and Greek, but we're looking to expand that specifically for other languages within the next set as well. Next slide. Okay, so to evaluate that, we have this table here and runs in which we've done in queries. So we have it for Arabic, Greek, and then we also had English probes. So originally we seen that the Greek retrieval failed completely with no language, with zero language match or pretty low. This is because the model was capturing semantic similarity, but since we had most of our examples from Arabic, the Arabic examples, it was mostly getting the model was capturing the semantic similarity from that data set. But then once we introduced the language aware routing, as discussed above, we've seen the Greek performance improve to perfect language alignment. So currently, when we get specific questions within Arabic and Greek, we see the language match rate is very high. It's very great within its data set homogeneity rate, in which it's able to route to the specific topic and domain, and also provide great relevance and ranking. Just to wrap up on this, we also did have some quick English probes. Currently, in the beginning, we did not have training data for English, so we just did probes within specific queries that we set up, just to test this as well on that side. But yeah, so we were able to complete that language aware routing and then basically do that without retraining the model on that side.
Cool. Awesome. Thank you so much, Justice. I believe the next one is also Fan eval task 2. I think that this might be Dianze. Let me check. I think they're not here tonight. Yep, they're not here. So we're gonna skip to task 3.
All right. Hi everybody. So this is the first time that we are presenting. Last time we missed a meeting. So to give you an idea what task 3 does in a nutshell, every day we receive 2 pieces of information. We receive text data about a stock and also price data about a stock or digital currency. And we have to predict whether we want to invest in this stock or in this digital currency, whether we want to be neutral or whether we want to sell our position. This will be a competition that will be evaluated via some live tests over a period starting at the end of the month. And it's more like a market timing exercise where we have to build a model that's pretty good in timing Tesla and Bitcoin in particular. These are the test assets. And as a group, we had 2 ideas. First of all, we want to do this via with an agentic framework. There are a couple of framework as open source available, so we replicated that, but they use pretty naive tools. So we want to give this framework more powerful tools in order to improve the performance. And one of these tools is enhanced sentiment analysis. The current sentiment analysis is pretty naive, and our idea is that we want to look at the sentiment analysis from different dimensions. And on the right side, you see the graph. We received the last day news, and this news has different sections. And we want to evaluate this section in isolation and then get an average sentiment We hope that with less context, the models are able to uh, to yeah to find more details in the last in news to obtain a better evaluated sentiment. And we also will invest some time into prompt engineering. And something which will also be very interesting is also to look at difference through time. This is why I put there a timeline, and we will compare the sentiment that we, for example, computed for January 4th with the sentiment that we computed for January 3rd, and we'll compute whether there are any differences in the sentiment, and hopefully this can also give us some trading signal. So next slide, please. Another idea, another tool that we want to give our financial decision-making framework is an enhanced technical analysis tool. Right now, our basic framework only computes pretty basic technical indicators. They're not really that widely used in the industry. So instead, we want to build a machine learning model that learns on the cross-section to give a classification whether we should invest in Tesla or in Bitcoin, given on the patterns that it learned across the whole market over a historical window. For this, we retrieve external data from the S&P 500 via Yahoo Finance. We build a pretty standard machine learning model that learns on the cross-section, so on all 500 stocks. We also build it so that it can do online learning during the competition, so that it's always updated with new data. And then we, for example, predict whether we want to go long or short in Tesla. So next slide, please. All of these tools are still in development, especially and also integrating them in the financial decision agent framework. So right now we only have preliminary results with the basic tools that we are using. And in this table, you can see that the agentic framework in the first row has relatively low return, but it has really low volatility. So the risk return ratio, the Sharpe ratio, is really competitive and really high. So that's something that we would like to see in the industry. Also, the max drawdown is very low. So investors who are not really risk averse, they would be very happy. But on the other side, if you're a young student and you want to go long and save for retirement, you would probably prefer the other strategies that there are on the table. Just buy Tesla at the beginning of the period in 2024 and stay long in it, and you have really high returns of 114%. But but you see that your max drawdown can be much, much higher. So you have to be much more risk averse. Yeah, that's all for today. We have to integrate our ideas now into the framework, and we hope that we can improve our returns.
Cool, awesome. Thank you so much, Max. Really nice to see what you guys are doing in the brand new FinEval lab. I believe the next one is Hype.
Yeah, hi. Yeah, I missed the last meeting, so this will just go quickly over some of what the hype person place relation extraction is about. So it's on multilingual historical documents. These are coming from OCR scans. The task is to given a document that's with annotated entities, person and location pairs, just to pull out two relation types, whether a person is at a location at the time of publishing, or if they were ever at the location being discussed. Let's just move on to the next slide. So this just graphs what I pretty much just said, just to give a more visual look at it. Next slide. So these are some examples of the annotations. So as you see, basically this is extracted from one of the example texts where you have the person, the place, and then whether they were at or they're currently at that time of publishing. Next slide. This gives a more visual how the data comes through and some label distribution of how it's set up. It's somewhat of a small data set we're given. Only about 100 or so examples across 3 different languages. And that's actually not German, it's Luxembourgish, I think. And then yeah, so the idea, and this is a sandbox data set that we used to run some analysis. Just maybe go to the next slide. All right, so yeah, so some observations that I made. So one of the first things I did was to just take a look at the data and try to look at what articles we got, because these are historical texts from newspaper articles. They can range as far back as to the 18th century and then up into the early 20th century. And so the language is all over the place, and there's not a lot of data. And so I just read through some random articles that were there and tried to identify some of the common patterns that I could find. And so, for example, like the role in a location, different action words that are being used, and so forth, and things that could aid in like signals for the person and location pair. Just go to the next slide. So yeah, so some what I found from just some basic simple heuristics, just just to have like a more of a floor for comparing other methods that would explore, just looking at the distance between different the person and place, and it showed the strongest signal, but it wasn't really that strong still. So that is sort of validated some of my ideas on perhaps the structure of the article and the sentences and so forth that are in there carry um, more provide more information about um, how the person and location pairs are tied together. The next slide, please. So some of the ideas that I had was to take some prompting approaches, and then try to extract whatever features I could, and perhaps arrange them into a graph. Uh, and then in one of the office hours, I think it was Jason that suggested looking at a paper called Flying Squid, which has a interesting approach of how to use just different checks to sort of extract some weak signals from the data, and then sort of use those as features to uh, run on different methods and so forth. So I'll be working on that going forward. Then I also was interested in, if I could arrange this into a graph, perhaps do more advanced things such as a graph intension network. Let's go to the next slide. So yeah, so this, I think I kind of discussed this already. Just if I have part of my perspective is that perhaps I could extract some information based on the relationship between the data. Maybe the next one. I think we're almost done. Yeah, so I came up with a way to sort of just to use like a dependency tree to get some more information. Next slide. And here's an example of how it might look if you take the different sentences and see how they could link together. And next slide, perhaps. I think it's that it. I think that's it. Yep. Thank you.
Cool. Awesome. Thank you so much. The next group presenting is ImageClay AI for Agri.
Hi, good evening, everybody. My name is Lucas. I will be going through kind of the overview here and what our team has done, myself, Hai Kung, and Ignacio. We have identified 3 experimental areas that we're pursuing. So we're all kind of working in parallel on our different experiments. So we'll each take a slide and discuss those experiments. Okay, just to give the overview before we get into the experimental work that we've been doing. The data set, AgriPotential V2, is a Sentinel-2 satellite image that captures both RGB and multispectral bands. And it's used for predicting agricultural potential. So how high of quality is the land that's captured for different crop types. You can see the key features here. It's a pretty large data set. One important piece of this is the data is labeled per pixel. So each pixel has a score, essentially, for the potential. And so there's also multiple crop types available in the data set, with the challenge or the competition being centered on the viticulture. Okay, so let's get into the experiments. Next slide, please. I'll hand it over to Ignacio for this one.
Yeah. So for this model, we base our experiment of a paper called TS-BIT, which is basically, as shown in the image, a two-stage transformer architecture where we have one transformer encoder for the temporal attention and another for the spatial attention. So for the results, we achieved around 76% of validation accuracy. And when we test this on the test data, it showed around 59. So yeah, a few more details about the model. We use patch-based tokenization. We also use a fixed temporal encoding based on the timestamp. This is a little modification from the Sham paper in which they also use a learnable encoding. So yeah, then the two-stage transformer. We also use multiple class tokens, one for each class, for each potential class. And for the training, we use a weight composite loss in which we use the cross entropy, but we also weight the ordinal loss, trying to to reduce the distance between incorrect examples. Yeah, then in the image is the basic architecture of this model. We don't use the classification head, we use just a segmentation head, which is basically a decoder data for pixel level prediction. Next slide, please.
Okay, so the next model I'm calling patchwise VIT without time. The training accuracy for this model is 83%, but this is a per pixel. An important thing, maybe I should have discussed this in the overview, is the accuracy for the competition is plus or minus 1 off of your class that you predict. So for example, if your model predicts a 2 and the true label is a 3, it would be counted as a success. So a couple of differences between the previous model and this model. And the big difference is that I chose to ignore time in this. So I'm skipping over that information to try and, without explicitly stating that the time is a factor here, seeing what kind of relationships can be drawn from that without designing the model around the time. So it also relies on self-attention, where it's a patchwise model, but the patches are globally referenced across the different images. And yeah, so this slide, I think I updated this a little bit late here. I was actually able to run through the leaderboard accuracy and got an accuracy of 49. So I have a couple of opportunities for improvement here that I'm working on. And the biggest one that I'm curious about is evaluating, including unlabeled data in this, because the typical image has maybe 20% of the pixels labeled. So there's a large number of unlabeled pixels. So yeah, that's it for this one.
Yeah, my name is Waikang, and we're almost out of time, so I'll be quick with this. So the final model that we evaluated is a UNet with a temporal attention encoder. Now, the validation accuracy is 80, and on tests after submitting to the leaderboard for this model, we got 57. The specialty about this model is we encode time as the number of days offset from the initial number of days, but this still did not beat the baseline using only UNet. So the next steps that I would try is probably to strip out the time dimension and just treat it as another channel. So yeah, that's it for our team's experiments.
Cool. Awesome. Thanks so much, guys. The next team presenting is ImageClay caption.
Hello everyone. Yeah, I'm Yuwen. Our team, Bowen, Ritash, work on the image CLEF caption task. First, I will give a quick recap. Our task is to automatically understand the radiology images by detecting clinical concepts, generating accurate captions, and providing human interpretable explanations. So we have images like X-ray, MRI, CT, so a lot of different type of radiology images. And the first task, concept detection, is to predict the UMLS concept unique identifiers directly from the images. The evaluation is the F1 score. The task 2 is caption prediction. It's generate clinically accurate radiology captions for each image, and the evaluation is like a comprise of like 6 metrics. And the task 3 is explainability, is to provide a human interpretable justification for captions on small subset of images. The evaluation is manual scoring by a radiologist with a score of 1 to 5. Next slide, please. Yeah. So for the first task, concept detection, we tried different architectures. First, for the baseline, we use the dense night 1-to-1 and efficient night BO for a simple ensemble, and also we tried KNN. For the standalone models, we tried Convenext, V2 base, Biomed Clip, and dense night. Then we did the juice stream with Convenext V2 and Biomed Clip. We fuse them through the cross attention bridge. Then we also did the ensemble. We did both 2-way and 3-way ensemble. For the 3-way ensemble, we used the Convenext, Biomed Clip, and dense night. The key innovations and optimizations are the first for the training, we use software asymmetric loss to downweight the massive imbalance of negative labels and focus on difficult to detect positive concepts. We also use generalized mean polling to allow the network to actively adapt to fine-grained macroscopic textures. For the inference, we use the test time augmentation. And for the post-processing, we use the coordinate ascent label thread holding to optimize for the global F1 score. Next slide, please. Here's our experimental results for concept detection. For the baseline 1 KNN, we got like a 0.54. And for baseline 2, the simple ensemble, we got 0.46. Then for the 3 standalone model, they have like a very close F1 score, around 0.5 to 0.58 to 0.59. And for the dual stream, we got a 0.59. It's between the convex and the bell clip. Then for the two-way ensemble, it's higher than the dual stream. We got 0.5941. For the three-way ensemble, we get 0.6061, which is higher than last year's top team, 0.5888. Also, Bowen tried the fine-tuned VIM, which used 27 billion parameter gamma-3 model. He tested in the 2025 dataset and got a very high F1 score. Next slide, please. Bowen will introduce this part.
Sure, yeah. These are results for the caption prediction. So baseline model is KNN. Retention is not here. So KNN plus TF-IDF. And so the baseline model, the scores are quite a bit lower than some of the top teams from last year. And also Ritesh also tested Quint3, which is another VLM model. For the first one, he didn't train the model, he just did zero shot. So as you can see, the score also is not very high. And he's currently training Quint3 with fine-tuning. And also he's currently training BioClip. And they're currently running. As for Gamma 3, it has the Rouge score is a little bit lower than the top scores from last year, but the BERT score is quite high. So the Rouge score is more of a direct comparison of the overlap of the words between the ground truth and the generated caption. So that one's a little bit low, but the BERT score is more of if the meaning is similar, and that one is a bit higher. Next slide, please. So this is like a flow chart through the fine-tuning process of Gamma 3. So you take open source base model from Hugging Face, the Gamma 3 model, and the base tokenizer. On top of that, you add the medical vocabulary, the CUI codes, to get the extended tokenizer, and then also did quantization, and I did fine-tuning using LoRa, which is additional small trainable adapter layers on the fixed base model. So you would train those adapter layers, and then you would do batch inference on that. The image below is an example of the prompting logic. So there is a system message which basically you're telling the model that it's a radiologist that understands scans, and the user prompt is to create a caption and a concept, and then the assistant output is is an example of what the model would output. In this case, a CT scan image. Next slide, please. So this is an example of the output of the model compared to ground truth. So if you see the left example, it's very, very close to the ground truth. It's basically word for word, except just missing like a fine detail in T2 at the end of the sentence. But other than that, it's like basically word for word, very good. The concepts match up as well. And then the second example, the concepts also match up, which this model has a very good score for concept detection. But in this case, the caption is a little bit more complicated and involved. So the caption is not as accurate. Yeah, and that's it.
Cool. Awesome. Thank you very much, guys. Great job. The next team is ImageClay Gans.
Hey everyone, I'm Samir from the ImageClef MedGANs team. So we're doing subtask 3. It's the privacy preserving CT slice generation, and I'll just do an overview of the task just as a brief refresher. So AI for medicine is extremely helpful, but due to privacy requirements, it's difficult to obtain a large amount of data needed to train a lot of these models. Um, and so collecting sufficiently large data sets for training these models is still a big challenge just because of all the privacy laws around patient data. And it's slowing the progress in developing like these advanced healthcare tools uh, for medical AI. So this is where like generative models can come in because now generative models are at a point where they can create realistic enough images that can be used to train the AI. So yeah, so they can generate realistic looking data that resembles true medical images while not being tied to any specific patient. So the problem before was that uh, due to patient privacy, you couldn't use this training data, but now with generative AI, we can make photos that are not tied to a patient at all and can be used to train the AI models. But the big thing here is that the synthetic data needs to be free of any like fingerprints from the real patient images. And so the overview is our problem is that we need to develop a model capable of producing these realistic and diverse images while also preserving patient privacy. So next slide, please. So as a team, we've been kind of going through a bunch of different methods for generating models. Um, and so one of them is flow matching, and we've got some pretty good results with flow matching actually. So like on the right, you can see like an example of a real image and like the two generated images that we have. Um, and this is just with the batch size of 4 and like 159 epics. Next slide, please. And then, so this is our results from using diffusion. So also very good. And again, this real CT, these are lung CT scans, by the way. So it's the real lung CT scan on the right. And then on the left, these are the generated from our model. This is a batch size of 32 with 300 epics. So diffusion takes a little bit longer to train with a larger batch size as well. And we've tried a few other image generation models as well. Um, we didn't really have a lot of success with GANs in the beginning, which is funny because that's the name of this task, but we can use any generative model that we want. So right now we've found a lot of success with diffusion and flow matching, so we're kind of going down that path. And then we also tried an experimental like drifting model, which like there was just a new paper on that recently that which we tried out, which worked kind of well, but not as well as diffusion or flow matching. Next slide, please. So we've been able to get some realistic images, but we haven't really implemented the privacy preserving part of this task yet. And so the way we intend on implementing this privacy part is using differential privacy. And so differential privacy basically injects Gaussian noise at every training step. So it'll mathematically, it'll make the new generated image not tied to any specific patient image. So by inserting this Gaussian noise, um, it makes the generated images more private than they were before. Um, but when we do this, it requires a lot of VRAM, lots of training, and way larger batch sizes. So if you remember, we're using batch sizes of 4 and 32 in those previous models. And so some papers recommend using a batch size of 4,000, like over 4,000 for using differential privacy. And so these are some examples of what we tried out first. And we don't have it on this slide, but this is using a batch size of 32. So we're still using a smaller batch size, and that's why they look kind of low fidelity and pretty messed up. Like this is not what a lung CT scan is supposed to look like. Um, but yeah, next slide, please. So yeah, so for our future directions, we're gonna keep trying to improve on that. And I think Rich is here to go over some of this Canon
Yep.
methods too. Yep.
Hey, so I'm Rich. Yeah, so we're basically shifting our focus to privacy now. Um, and one of the more basic methods we wanted to implement first was just a KNN anti-memorization method. So this would be basically just encoding the training set and then penalizing each sample that falls too close to the real examples that we were given. And that would happen during training and during inference. Um, and then also we wanted to try to extend that to the manifold as well. So it would penalize proximity more broadly. Um, and then just real quick as well. So we also wanted to focus on like a structure focus loss. So instead of just looking at like a broad pixel level fidelity, um, we would look at like bone structure or like airway patterns or low boundaries. So like things that are more specific to the images, um, or the slices rather. So those are the two things that we're working on. And then we'll also try to explore some novel techniques as well, like noise multiplicity, uh, X risk with KNN, and then also maybe augmentation multiplicity. So that's kind of it for us.
Yep.
Cool. Awesome, guys. Thank you so much. Great job over there. Really realistic images, at least the first one.
Thanks.
Thanks.
Cool. Next one is ImagePlay Media Medi QA.
Hey everyone, I'm Charlie. Just to give a quick background on this task, the challenge focuses on automating brain tumor subtype using multimodal clinical data. So that is going to be MRI sequences, whole slide pathology images, as well as free text pathology reports. The catch is that not all of those are always available. So usually there will be either an MRI or there will be an MRI, a WSI, or a whole slide pathology image and a report. So it's either just an MRI or all three. But you essentially have to handle both cases. Um, so that's the catch. And to make it really interesting, you there it's that's what they do. They try to make it reflect real world scenarios where you don't always have all the data available to you. Um, so just a few updates. And the reason I'm giving updates is because we don't actually like the data just dropped like 3 days ago for this task. So yeah, it's been a lot of fun. All right. But anyway, we actually revised our originally proposed architecture. So our last proposal was, oh, we're gonna fine tune these three, models using QLoRa and, it was a lot of stuff. And we realized once they pushed back the release date that we weren't gonna have time to do all that because they did not push back the due date. So yeah. So yeah, data, just for reference, data was released on March 27th and the development phase ends on April 27th. So we've implemented our starting approach fully. It's actually on the next slide, but we can stay here for a minute. We also built a RAG index using, believe, 6 or 7 different sources. And due to the sensitive nature of the data, in order to obtain a copy of the data, we actually had to fill out paperwork. I believe there's an IRB involved. So we are currently waiting on that approval to come in before we actually start processing the data. Next slide, please, Murillo. Thank you. All right, so the RAG index uses the WHO 2021 CNS. It uses RADLEX, which is essentially just a dictionary of radiological words, essentially. EANO, oh, I put EANO twice. Oh, I put EANO 3 times. Okay, that's great. Sorry about that. Yeah, so there's EANO, there is BRATS, there is. Hold on a second. I can pull up the rest now. Have it written down. But long story short, that's being used to generate a RAG index using MedCPT and FICE that is being used by our downstream models. So what we're doing is we are taking the input case, be it an MRI, WSI, or a port triplet, or just an MRI. If it's just an MRI, we're passing it to BioMedClip, and we're having it generate a text caption for it. If it's all three, then the MRI and the WSI go to BioMedClip, and then the report itself goes into Sci-Spacey and it gets negated. Then it goes into a custom modality handler that we designed. It's essentially a glorified data class that takes in a bunch of this information and decides, okay, this is how we're going to handle this or this. And it's essentially a configurator, if you will. It configures downstream tasks based on the input. And that whatever the result output of that is gets passed to adaptive RAG retrieval. It uses multiple queries multiple repeated queries, and the number of repetitions depends on the type of data. But yeah, it gets multiple queries, then that goes to FICE, and that returns the top passages. We're going to be using DSPy compiled reasoning using VLLM with Llama 3.370 billion on port 8,000 rather, Quen 2.572 billion on port 8001, and an R1 distilled version of Llama 3.370 billion on port 8002. So for full cases, each model is doing 3 queries each, just to try and normalize. Every time you do a query, it'll be different. So to try and normalize the response or get an average response out of it, you're doing repeated queries. But for MRI only cases, obviously it's going to be much less certain about what it's doing if it just has the MRI. So we're using 5 queries per model for a total of 15. After that, it will ensemble the three model outputs with priority placed on R1's model output because it uses reasoning. And then the output will be classification, reasoning, so why it did what it did, and then a confidence score as well. That's all we have. We haven't actually gotten to test this fully yet, but it is implemented and it is sitting in our computers waiting to go. So that's all I've got.
Cool. Awesome. Thanks so much, Charlie.
Thanks, Merlo.
And yeah, kind of annoying that some competitions release the data like in March or almost April. But it is what it is. Cool. I think next one is image clay multimodal reasoning. And I think this is the last image clay one.
Hi, everyone. Yeah, so our team is working on the image CLEF multimodal reasoning, and we design a workflow that can answer STEM questions from exam.x dataset. So for last year's competition, the top topics didn't just feed the image directly into a model. They used a multi-stage pipeline. So basically, we can see that the team MSA it had a perception step where they used vision language models to generate captions and also applied OCR. to extract any text from the image. And the context drift team used a simpler pipeline, but put more emphasis on prompt design and reasoning quality. So we found that we might need to also design a multi-stage like perception and reasoning because the limitation of the ability of the models. And next slide, please. Yeah, so based on what we learned from the last year's top teams, we designed a basic pipeline that also separates perception and reasoning into two stages. In the first stage, we focus on the perception. We use the Germ 3.4b as our vision language model, and we also incorporate OCR so that we can extract any textual information from the image. And we combine the output of the so we actually fit the output of the OCR and the original image into the vision language model and get the caption. In the second stage, we feed this information into the large language model. Again, we use German 3.4b as our baseline model to generate the final answer among A, B, C, D, or E. And we got some initial results under different configurations. We can see that the model performs better than randomly get the choice, but the accuracy is not very high. And we can also see that there is an example of a Chinese biology question. The caption generated by the vision language model in zero-shot setting contains several obvious errors. So in the A and B, or in the B and C, the second letter is E. However, in the translated options, it's a Chinese letter, so it's obviously incorrect. So we found some limitations of the vision language model. Next slide, please. And after our initial German-based baseline, we also run experiments with Crane 3.59b, and the results were much stronger than the previous one. And our current overall accuracy is about 0.84, which gives us a much better starting point than the baseline. We also observed that the performance varies quite a lot across several categories. For example, in terms of the language, the model performs very well on Bulgaria, French, but it's relatively weaker on Polish, English, and Chinese. And we also look at the error patterns. According to our analysis, many failures are not simply due to perception. Some of them comes from reasoning errors, and some models became very verbose, repeat the reasoning step, and then exceed the token limit. So there are also some metadata issues and annotation noise. So based on our current work, the next step is to try some reinforcement learning methods like GRPO. And the idea is to improve models' reasoning behavior directly instead of only changing the prompts or OCR. We also want to design rewards that encourage not only correctness, but also shorter and concise outputs. And then we also plan to compare Queen 3.59b with a larger Queen 3.527b version to understand if the later performs better. Yeah, so that's all.
Cool. Awesome. Thank you so much. I
Thanks.
believe, yeah, no problem. I believe the next group, I actually have to refresh. I think our show is gonna present because he has a hard stop right now. So we're gonna actually go to Pan.
Okay.
Yeah, all yours, Harshal.
Can you hear me?
Yes, sir.
Okay. So, hey guys. Yeah, I'm working on the pan task, and specifically I'm working on the void conf task, which is basically just if I'm given a piece of text, I have to classify it as either human authored or AI generated. It's pretty straightforward, but can be difficult at times. And this is an overview. The data I'm working with right now is just the training samples and the validation samples. The pan, I guess, organizers haven't actually released the test samples yet. So as of right now, I'm just training on the test set, on the training set, and then testing on the validation set. But I think either this weekend or next weekend, the test set should be released on Tira, so I will be evaluating on that soon and getting new scores. But yeah, just as a caveat, the validation and training samples are basically from the same distribution. So it's like the same models generating the text, and it's like the same topics and genres. And the test set will have more out of distribution data because of different AI authors as well as some obfuscations. So some of the test set will be different than the data I'm currently testing on, which is important to note. So yeah, just to keep that in mind. But yeah, here are the different metrics that I'm actually being evaluated on. The biggest one is just the receiver operating curve area under the curve. This is like the main metric, as well as some other, again, secondary metrics like beer score, C1, F1, and F0.5. All of these are just measuring, again, how good am I at classifying text as either human. Oh, what should we say? Next slide. I forgot. Murillo. Yeah, I'm just talking to the screen. But yeah, again, listed are here. Here are the metrics. But yeah, like these metrics basically just saying how good am I at classifying something as human generated or AI generated. And yeah, they're all pretty good metrics. All are testing different things, but overall, a good solution should have a high score on all of these. And yeah, I've been mostly just measuring my progress off the ROC AOC, but I'm also keeping track of everything else, and it's making pretty good progress so far. In terms of, I guess, how my solution has progressed, I kind of started with pretty basic solutions, just traditional ML, so logistic regression and like an LGBM model, just to see how good do these like baselines perform compared to, I guess, like, I don't know, random chance. And then from there, I've transitioned to more, I guess, you could say complex solutions, but arguably it's still pretty simple, where I just work with a transformer and I use either some kind of fine tuning like LoRa or just zero shot classification just to see how it performs. And as of late, I've switched to using large language models plus a LoRa fine-tune as, I guess, my most optimal solution. And in this case, I'm using Qwen 2.5 as my model. Next slide, please. So yeah, as I was saying just now, right, the best solution I've had so far has been to use Qwen 2.5, 1.5b, a pretty lightweight model with a LoRa fine-tune in order to actually, again, make it a classification, give it a classification head for picking between AI-generated text and human-generated text. So again, I just used the training dataset split provided from the PAN lab, and I've just been evaluating on the PAN validation split alongside outer distribution datasets in order to actually capture, okay, how well is my model, again, um, adapt to data I hasn't seen before. Because in the test set, I will be seeing, again, models that are authors that I haven't seen before, as well as obfuscations that I haven't seen before. So yeah, with just this raw performance, I've been able to see some pretty strong performance on both in distribution and out of distribution data, which honestly is really surprising for me at first. But yeah, here are the metrics on the right. HT3 and RAID are two different, again, out of distribution data sets that I've been testing on. You can see that HT3 and PAN both have really high, again, scores for all the metrics. For beer, you want the score to be as low as possible or as close to zero. So 0.0019 is really good. And everything else you want to be close to one as possible. So again, these are really good scores. But yeah, it is struggling a bit on RAID, which was another out of distribution data set. So there was some work to be done. But overall, it was a really good, again, first shot at this. Next slide, please. And since then, I've continued to like again iterate on this method. I've been trying to just find more out of distribution data to actually test on and see, okay, how can I push my model to its limits? And so far, it's still been holding up pretty well, but these two data sets, Mage and the AI detection pile, both have proved pretty difficult. So I guess next steps for my project is going to be like looking into these data sets, figuring out how can I train on these data sets to improve performance. And again, this is generalized to other distribution data sets. I guess the whole goal for me is to make my solution as robust as possible, and it should be able to, again, see any type of AI-generated text or any type of human-generated text and classify it as such. So yeah, that's pretty much where I'm at right now, but pretty good progress so far.
Cool. Awesome. Thank you so much, Harshal. Appreciated. And great job on the task as well. Awesome. Cool. Next up is Joker. I believe Rusty is here or someone from the team.
I'll be presenting.
Oh, cool. Adam. Nice.
Hi, everyone. So the task is pun translation to French and Spanish. This is the Joker task. Joker project. So in terms of the update since the prior iteration, the motivation of our approach comes from a translation scholar named Peter Lowe, who argues that a joke should be translated as a joke and not word for word. And that sounds obvious, but my earlier system wasn't doing that. It was finding the closest French word for each English word, and as a result, the sentences often lacked humor, so the entire orientation of the system shifted towards preserving humor as the primary goal. I also shifted to focus on a better detection of what the pun words were. So before I could translate a pun, I needed to find where it was. In my old system, it was bad at this. It would sometimes pick filler words like the word what or they as a pun instead of the actual joke word. So I made two fixes. First, I filter out common function words so that they can't be selected. And second, I gave a bonus to words near the end of the sentence because that's almost always where the punchline is. Next, when it came to translations, I have shifted to translate phrases in chunks and not word by word. My old system translated by individual word, which in the case of a phrase like field trip, it would get split into the word field and the word trip, and translated separately gives you nonsense in French. Now, I send full phrases to translate at once, so the word or the phrase field trip becomes the natural French expression. This matters because if the setup sounds broken, the joke is dead before the punchline even arrives. I also modified the approach to recreate the feeling of the joke and not exact wordplay. A perfect homophone pun in English almost never has a direct equivalent in French, so chasing that usually fails. Instead, my system now classifies the vibe as the joke, whether it's dark, absurd, or ironic, and it constructs a French punchline that delivers with the same emotional beat. I want to be honest, though, that this step is currently using some hard-coded template examples. The structure of the punchline is fixed and only the noun at the end changes. It works, but making this dynamic is the main thing that I need to fix next. Finding the French words that sound or mean something similar is where I try to approximate the pun. And I use two resources. One of them is Lexique, which is a large French phonetics database to find French words that sound like the translated pun word, and WordNet, which is a semantic database to find French words that mean something related. As an example, the goal is for a French word to carry multiple meanings. So a word in English, offal, which is spelled O-F-F-A-L, carries both the meaning of organ meat and also the English word awful, spelled A-W-F-U-L. When it comes to score words as candidates, the system finds the candidate French pun words and it needs to pick the best one. My old system just took the first candidate and scored it above a fixed cutoff. Now I score every candidate using a composite metric based on Peter Lowe's framework, which weighs a few things, including how well the candidate preserves both meanings of the pun, how strong the phonetic relationship is, and the type of pun structure that I'm dealing with. So the best candidate wins on multiple dimensions. Clearly, there's a known issue with the pipeline. I leverage a polygon solver, which is Lowe's approach or algorithm, to find a French pun candidate, but right now the rewrite layer isn't using it. It falls back onto that hard-coded template, which is an area of further work. The result, though, currently is that the output appears to be a joke that native French speakers can actually understand as a joke. Now, as somebody who isn't fluent in French, I used large language models to determine if it seems like the output is a joke, and they said that it was. And with that, I conclude.
Cool. Awesome. Thank you very much, Adam. Appreciate it. Next one is image clay, animal clay.
Hey, my name's Evan. So I'm working on Animal Clay with Anthony, Snigna, and Dante. And so just an overview for this competition. So Animal Clay is about clustering individual species. So we have loggerhead sea turtles, Texas horn lizards, salamanders, lynx, and it's much more complicated than last year's competition because for this, we have to classify or cluster each individual species, and then we're evaluated by adjusted rand index. And so the baseline script for this is the competitors, they released mega descriptor baseline, which what it does is computes the embeddings of each of the species and then uses cosine similarity and then turns that into a distance. Currently, what we have so far is we have a public leaderboard of 0.379 ARI, 12th place, and our goal is hopefully to get above zero point 0.7 ARI. Next slide, please. So there's a lot of different moving parts in this pipeline. So we have the input images for each of the different species. There's a lot of different species aware pre-processing. So for each species, it can be a little different. So for salamanders, what we're currently doing at the moment is using SAM3 to segment out the background. As you can see on the right, there's a lot of noise with the background. And this is actually a test that I was doing using the actual spots to help identify different salamanders. Um, a lot of test TTA, so we'd flip over the image left to right and normalize those embeddings, orientation correction, and normalization. There's main global embedding models for this, mega descriptor L and MUID. And then using these two models, so we want to look through and find, for this salamander, let's find the top 300 closest cosine similarities from this image to other species. And so we're using that 300 budget shortlist and then using local matchers such as Superpoint plus light glue using a light, and then using these feature matchers to help, which is much more computationally expensive to try to like find more local features to help identify this animal. And then using score normalization, so just a weighted fusion of the global embeddings plus the local matching of all of the different key points and matchers, and then using those to cluster the graphs and then get an output ARI score. Next slide, please. So this is just a part of the key point matching. So what we're doing currently, one way we're working at local matching is using confidence weighted sums. So a lot of the key points, they're extracted with superpoint aligned, just different ways to match, find interesting features from one image, and then find interesting features from another image. And a matcher like light glue, it's going to find very interesting. It's going to find both matchers in each image, and make connections to those image, and it can return a corresponding anchor and a confidence score of how confidence it is for this match of pairs in an image. And so what we can do is use low confidence. We can filter out low confidence matches for an image. And then with images with higher confidence, we can include those in as well. And then using multiple matchers and features to just make it more robust. Um, and then next stages as well, we're currently looking into 3D representation of images as well. So there's a model, Magic Pony, I know Anthony and Snug and I are working on, is creating 3D representations of animals to help with the re-identification. Yeah, thank you. And here's some, sorry, I forgot this was in here. These are some of the, this is MuID and Dino V3 just visualized. So you can see on the bottom, you can see the Lynx image. You can see a salamander. It's very hard to pick up, but you can see the salamander. Someone's actually holding the salamander with his hands, and then the sea turtle as well. So the MuID is very good at picking up texture in these images. With these sea turtles, they have these like weird like kind of coarse spots on them, like these patterns. And with salamanders as well, they have these many small spots. So both models working together pick up very different representations.
Cool. Awesome. Thank you so much, Evan. Really cool visualizations that you guys came up with.
Yeah, thank you.
Awesome. I think next one is board clay. Anthony.
Awesome. So today I want to talk about some of the modeling progress that we've made on the Bird Clay 2026 competition. So for those not familiar with Bird Clay is a competition that is trying to identify species of birds, amphibians, insects, mammals within these soundscapes. A soundscape is basically a long recording that's taken by a recording device that have been placed in here, the specific region, the Panatel Valley. But basically, we want to be able to identify when are things vocalizing, and if they're vocalizing, what species is it? So this year, there are 234 species across 5 taxa, birds, insects, amphibians, mammals, and reptiles. And so the goal is to go through these 60-second soundscapes. We have a limited CPU inference budget, so we're supposed to make these models that are fairly compact and able to run on small devices. Currently, the number one solution is at a AUROC score, which is the area under the receiving operator characteristic curve. This is like a ranking metric, which tells you whether you're doing well based on species that do exist there in ranked order. But the best score right now is at 0.94. Our best score that's been led by Murillo is at 0.918. So there have been a lot of submissions and quite a few models trained. So there's a couple of different approaches for building out these models. Really what you do in essence is you take a good big foundational model and you train a classifier on top of it. These models are typically taking audio, turning them into spectrograms, and then building some kind of vision model on top of this. Here we tried these clip level models. So a clip level model is taking the 5-second clips of audio and just predicting out of the list of species, which one is the most likely. So we use a couple of different models here. There's some CNN-based ones. There's a CVT-based one, which is like a hybrid between CNNs and vision transformers. There's some vision transformer-based ones. And we get a variety of different scores depending on whether we use the focal or the soundscapes, or some hybrid of the two, using a couple of kind of like iterative methods. So here the best model on the leaderboard is around 0.76. Then we go on to from a clip level to the sound event detection model. So sound event detection basically has these two arms. One arm is for predicting what species are going to be located within a small subframe of the clip. So you split the 5-second clips into smaller temporal regions, and then each of these regions you kind of determine whether or not there is a vocalization and whether what species it is. And you can do aggregation over this to go from a sound event, event-based model to a clip-based model. So here we have models that take advantage of, well, we use one base model, which is EfficientNet, a CNN, and we do a bunch of techniques that have been proven on the leaderboard. And here, the best leaderboard score goes up to about 0.85. And the last variation on this is based on a strong foundational model called Perch. So this is the Perch. It's a prototypical model, which means you have prototypes for each of the species, and the state space model, which is a way of making sure that vocalizations that occur of certain species continue to persist within a specific segment of audio. So this is kind of like a Kalman filter, or a Bayesian kind of updating within a soundscape itself. So this is an interesting approach. You just take the foundational model, you do some linear probing, you have some level of like consistency via the state model, and you have some of these prototypes that are being built using various mechanisms. I think you have like an attention-based thing. And there's lots of little post-processing techniques that helps bring the scores up from this base Perch score of 0.82 all the way up to this score of 0.192. So this is not the end of it. We have some future directions that will go modeling wise. So if you go to this last slide, yeah, I think one of the interesting directions we'll want to go is to use kind of token-based modeling, so kind of like a language model, but for audio. And for that, I think the only way to do this, in a way that fits the inference budget, is to use Mamba, in particular Samba. There's some stuff around source separation that I think is interesting, Mixit, and whatnot, that can be integrated into a language model-esque kind of approach. I think we'll do probably some separate modeling for low resource species like amphibians and insects. And then I think there's a lot of stuff that we can do to exploit the statistical properties of the unlabeled data using the models that we already have trained. So we have these pretty strong models on the leaderboard. I think we can use these to do some data modeling of the unlabeled soundscapes to kind of help this and bring this into whatever new modeling that we do. So that is what we've done for the competition so far. Thank you.
Cool, awesome. Thanks so much, Anthony. I just realized that using a model named Samba for a competition that has data from Brazil, it's quite appropriate. But okay, next one is FathomNet.
Thanks, Murillo. All right, FathomNet. So we're doing positive unlabeled detection in marine imagery. I'll go over a quick summary of the problem and then kind of what we've done so far. So we have about 6,500 images, and they're all 1080p and 4K, 32 different marine organism classes. Our training data is sparsely labeled, but the data that we're tested on is fully annotated. So here's a example data over here of the training data. And you can see there's some labeled stuff, but there's also stuff that's not labeled. And that's kind of the crux of the problem of being positive unlabeled. And I will get into that in just a bit. Current model architecture, we're using Vision Transformer backbone, so Dino v3, the 300 million parameter model, FPN NEC, which essentially creates feature maps from the backbone output. And then right now we've been using the faster RCNN head. It's 2 stages. The first one proposes bounding boxes, and the second one classifies and refines whatever's in that box. Metrics being used for the competition is the COCO mean average precision. And then our metrics that we're kind of using to judge our own models are there's a mean average precision on the validation data, class accuracy, IOU, so for localization, and then recall as well. Next slide. So first part, the backbone is pre-trained on general images, so like ImageNet. So there's a big difference in the domain between that and what marine organisms are look like, underwater. So by unfreezing the backbone, we can adapt to the marine domain. So we have our pretty much frozen model, which is the light blue there. So 4 layers out of 24 were trainable. And then you can see as we unfroze it, the mean average precision got better. So we found that by unfreezing all of them and doing some other things, so we have implemented focal loss and doing some strong augmentation on it with flipping the images and rotation, jitter and stuff like that. We have about 100% improvement between the frozen model and the unfrozen model. And class accuracy there is at 68%. That's a big step. We use the 640 by 640 images on these first ones just for quick iteration of being able to train the models quickly and see how our changes are affecting it. So the next thing we did, if you go to the next slide, please, is multi-scale training. So instead of using the 640 by 640 images, which when you make them 640 by 640, those small organisms, you've made them just a few pixels, wide now. And then obviously there's going to be a lot of distortion to that. So we kept the aspect ratio and downscaled the 1080p and the 4K images. So the 1920 pixel width of a 10K or of a 1080p image down to 1280, and then the 3840 pixels of a 4K image down to 1536. So by keeping them larger, we can preserve a lot of the spatial detail in that. So by doing that, we got a 12% increase in the mean average precision on our validation data. And then also, if you see it in the top right, the localization, the IOU got a lot better by doing that. And kind of what I found odd was whenever we look at the classification accuracy, is that the 640 by 640 images actually had better classification scores than the multi-scale training. And that's probably due to Dino v3 was trained at, I think, 518 by 518. And the smallest we're giving it is 1280 in width. So there's a really big difference between what the model was trained on compared to what we're giving it, or at least the pre-training. And then the ROI pooling, the region of interest pooling, behavior changes at higher resolutions. So there's some things that we can do by changing out detection heads to maybe DETR. And cross attention is a lot more resolution agnostic. So it could possibly avoid that issue. So that's something that we might try down the line, or that we've started trying down the line. Next slide, please. So positive unlabeled problem. So the top plot there is the recall at 50 or 0.5 IOU. So it's the fraction of the ground truth objects with at least one proposal that has IOU over 0.5. And so the region proposal network that's making those, we have a 99% recall at that. The second stage of the detection head is the classification, which is only at 18%. So you can see in the bottom plot that's a lot lower. So essentially what that means is that our model is, it knows where things are, but then the classification head is throwing away most of this stuff. And that's because we're training on data that is only partially labeled. So the model has essentially learned to suppress real detections. When we make our submissions on Kaggle, our highest is a 0.12 Kaggle MAP. The highest on the leader that puts us at fifth. The highest is a 0.3. So I guess everybody's struggling with it, which is good for us. Next steps: pick up aware loss. So using non-negative not pickup, positive unlabeled aware loss. So we're currently training some models exploring that. Doing some pseudo labeling, so using grounding dyno to label missing objects. We have the opportunity to do, or we started looking into student teacher approach, so kind of like a self-improving loop. And then also training on the multi-scale plus full resolution crops, because a lot of these annotations and bounding boxes in these 4K images are already really small, so that might help as well. But anyway, that's it. Appreciate it.
Oh, awesome. Thank you very much, Rob. Great slides. The next one is Planck, and I believe Alper will be presenting.
Yep. Hi, everyone. This is Alper, and I'll be presenting the progress of the plant clay task team. And as an overview of the task, the goal is to predict all the plant species appearing in test photographs, which often contain a bunch of different plant species together in the same image, as you can see on the right corner of the slide. And for this task, the organizers have provided pre-trained Dyno V2 visual transformer models, but these models are trained on single class plant dataset, as you can see on the top portion of the top right portion of the slide. And the training dataset includes over 7,000 plant species, and the test image set consists of 2,100 photos. And some of these photos are the pictures taken from the same exact location, but visited during different times of the year. And the performance evaluation metric used for the task is a multi-label F1 score. And last year, the SGT team placed second place on this task with an F1 score of 0.348. That's the private F1, and the public F1 score of 0.316. And we can go to the next one. So in order to predict multiple species on the same picture, when using a model that's designed for single species classification, most teams adopt a tiling approach where the image is split into multiple tiles, and each tile is fed into the model, and at the end there's like a voting aggregation done, and the tiles with the highest confidence in species probabilities are selected, and then that's how the final multi-label results are produced for each image dataset. And then again, this year's strategies are building on last year's findings, and the goal is to further improve the F1 score. And again, last year's results show that when doing single tiling scaling, 4x4 performed the best, since it produced tile sizes that were closest to the training image dimensions. And then this year, the idea was to combine multiple tiling resolutions together to get an even better score. And in the example, you're seeing like 4x4, 5x5, and 6x6 tiling schemes all combined together. And this resulted in a significant performance improvement. The F1 score went from 0.35 to 0.38. And then after that, picking the best version, we did some further perimeter tuning, and that resulted in a final score of 0.401. this part of the experiment. And next slide. And as another separate technique, we also looked at doing using a different type of model, which is utilizing the image similarity, using the Facebook AI image similarity library. And we built a k-nearest neighbor model and using the embeddings generated by the DynoV2 model. And this is thought to complement the results from the previous model. Since this is a completely different model, it would result in a overall performance improvement ensembled with the other model. And yeah, in this approach, we're feeding the tiles, query tiles, into the KNN model, and then yeah, that selects like neighboring species, and then it calculates probabilities based on this model, and then the probabilities from this model is combined with the other model using ensembling. And next slide, please. So we looked at different ratios, like the beta multiplier when combining the result probabilities from two different models, and then the best performing one was where we had 20% of the probabilities from the KNN model, with the 80% coming from the other aggregator for the multi-visit test images, and then for the single visit locations using the main one resultant best, like KNN was actually creating noise for those. And the overall performance improvement from this approach, it took the results from 0.4 up to 0.418. And next slide. So yeah, we tried other techniques too. I just presented the ones that resulted in the best performance improvement here. But as you can see, the progression of the results and our future next steps to further improve the F1 score mainly consists of doing some image border cropping, further model ensembling, and also incorporating object detection to further improve the performance. And that's it. Thank you.
Oh, awesome. Thank you very much, Alper. Great slides as well. Thank you. Next up is Long Eval.
All right. Hey, everybody. So I won't be talking as much about results for Longeval or Task 4 Longeval RAG tonight because we only just received the data on Friday. So right there with the MediQA people. We'll instead cover the approach and sort of what we're thinking for this task. So as a reminder, there's two parts to this Longeval RAG task. There's a question answering part where we're taking queries and pre-retrieved documents from the core scientific document corpus and answering the queries. And then there's a exact evidence extraction part where we're expected to provide the exact document snippets that support the generated answers. And so our general idea is to use an NLI cross-encoder for entailment checks. We basically atomize the query and evidence into facts that we're basically extracting from these pre-retrieved documents. Since we only have to consider 10 documents at a time for this question answering, it actually makes it a lot easier to do kind of more heavy lifting in terms of this fact extraction. So as such, we can kind of identify the relevant evidence using this entailment or contradiction checks, and both entailment and contradiction are really valuable when kind of finding evidence to support or reject a query being submitted, or a question being submitted in this challenge. This type of atomic fact-based scheme has been used before to actually evaluate RAG systems. So to evaluate like the factuality and faithfulness of RAG answering to the underlying corpus. It was used in Trek 2024. And so what we're essentially doing is just sticking that inside the pipeline in front of the generator so that we pass along the evidence that is already most supportive from the underlying documents. And hopefully that'll allow us to kind of game the evaluation metrics, which are really strict about having very faithful answers. Next slide, please. So this atomization or nuggetization, depending on where you've seen this described. We saw this example in how they were evaluating the Truck 2024 RAG tasks, where they were basically evaluating if they synthesize the answers from the correct facts extracted from document chunks. And this was actually, the paper itself was actually presented at SIG-IR, but it was based on the evaluation of the Truck task. And now we're being asked to implement a RAG QA system that does essentially what they were evaluating, right? Synthesizing explicit evidence to answer questions. So I think that this approach should do fairly well. Next slide. So a couple things that are interesting about this task is that we're not really sure how much longitudinal evaluation there's really going to be. We only see one snapshot in the RAG dataset so far. So it's unclear if we're going to really do any temporal-based query routing or any kind of like sophisticated time-based methods to consider like the timeliness of documents to the query. But that remains to be seen. But we can handle this with the method as we're moving forward. And then as far as the generation side of things are concerned, I have kind of a sort of a lame example here, where I've taken just a query that's kind of the spirit of Longaval, and then taken some fact snippets out of workshop papers from 2024 and passed them into Quen after doing the just a basic NLI with Deberta. And it does decently enough. It actually throws out the distractor that I threw in there, showing that it wasn't relevant to the question, and generates an answer that basically uses as much of the underlying evidence as possible. Obviously, we need to scale this up and try it on kind of the core data set itself. But we should be able to handle like instances where there are strong entailments and strong contradictions, where we need to give an answer that kind of goes both ways, or where there's an argument in the open scientific literature. So we're pretty hopeful that this will work. A few things that we want to look at on the NLI side are possibly considering like a scientific discipline specific NLI model, especially like the Cybert variants that have tokenizers that account for a lot of the jargon that you find in scientific papers. But we're still early days, so we've got some time to try and work through all of that. But that's where we're at. Thanks all.
Cool. Awesome. Thank you very much, Brandon. Yeah, sorry about the data again, but it happens sometimes. But glad that now you have the available data and you can start doing the modeling stuff. And I think this is the last one. So Quantum Clay. I'm actually not sure if we have. I think Pratik is presenting Quantum Clay, but I think he's in India, so I'm not sure if he'll be able to present today. Anybody from Quantum Clay here today?
I think Rusty's the other person, right?
Yeah, and I don't think he's here, right? Okay,
Yeah.
so nobody's here for Quantum Clay. We can end things a little early. Let me go to the next meeting. Okay, so next meeting is going to be April 20th, and it's going to be kind of like a modeling part 2. It's going to be really truly the last meeting before writing the paper, and yeah, basically wrapping up the experiments and everything. Maybe we're gonna change the meeting topic to paper writing or something like that. But I think that the next meeting should truly be focused on just showcasing results, like what results they have. Some people, like we saw today, their data was only released very late into the game. Like Brendan's saying, they got the data on Friday. So it'd be nice to see kind of tables and just collective results that we all came up with. So I think that for now we're settling the meeting as modeling results kind of part two, but more focus on results, just a bunch of ablation results or just final results that you have. And yeah, 3 slides minimum, 5 minutes total per team as well. Modeling overview, modeling approaches, and results. So very much focused on the results. And yeah, we're ready almost at 2 hours for the meeting. We're actually past 2 hours. So I'll keep questions offline. If you have any questions, feel free to reach out on Slack. Thank you everybody who presented today, and thank you everybody who stayed all the way throughout the entire meeting. Really appreciate it. And yeah, I will see you guys next month for the monthly meeting. Otherwise, ping me on Slack. Awesome. Bye bye.
Thank you.
Peace.